for coming today. And today it's a great pleasure to have Yukari Yamauchi as a speaker. Yukari is a postdoc at INC, and she graduated from University of Maryland. And she's working in this very exciting field of QCD finite density and trying to solve a sign problem, not only in QCD theories.
Wow, well, thank you for the very nice introduction. It's 10 times longer than for the Scott. Yeah, so today I'm going to talk about sign problems. It's a problem in lattice QCD, so I will say first, I should first say that this talk is the first half of this talk is based on this paper with Hyun, he's a graduate student at Maryland, and also Scott. So yeah, sign problems. So where does this? Okay. Where does this happen? So sign problem is a sort of a problem in lattice QCD. It's a non-perturbative method to compute various observables in QCD on the lattice in non-perturbative way. So for example, if we want to say compute the inner structure of say proton as a sort of by sort of quarks and gluons, and you find that, okay, so you want to compute the PDFs or maybe hadronic tensors, and you find that in Avery, you will see some sort of what's called a real-time sign problem in computing that on the lattice. Or if you want to say, for example, study the some transport properties of QCD that you see in heavy ion collisions, then maybe you want to compute, say, okay, I want to compute shear viscosity, and then you want to do it on maybe lattice QCD because the system is very strongly interacting. But then because of this real-time dynamics of this nature of this transport coefficients, again, you see what's called the real-time sign problem. Also, if you want to compute the equation of state of QCD at finite density, then you have, again, finite density sign problems. So there are sort of two main kinds of sign problems in lattice QCD. And for these examples, for example, for PDFs, there's a particular sort of almost solution to this problem called large momentum EFTs. Also, for this kind of very low energy transport coefficients, there are ways people are trying to sort of method there people are studying to get to those transport coefficients by doing some Euclidean calculation that doesn't involve in sign problems. But
what is the connection with large momentum EFT?
For the PDFs.
Okay.
So they sort of boost the frame to the close to the light cone, and then somehow where they don't have sign problems, then they can compute PDFs and come back to that. They can evaluate PDF in that way. Yeah, I don't know if they can get complicated 2D or 3D PDFs. I don't know much about them, but if there's at least particular sort of methods to address those issues. It's cool. But there is no generic solution to this lattice QCD sign. This is what I'm trying to do. So okay, just to say a bit more about the sign problems. So again, this is a problem on lattice QCD, and the goal of this lattice QCD is to compute this kind of some expectation value of some function O on the lattice. So first to do this, you sort of discretize your space and time in classical lattice QCD calculation, and then say have a grid, and have quark fields on the sides, and then gauge fields on the rings. And then I write down path integral for this lattice QCD, and then by this important sampling, that sort of obeys using this distribution with this Euclidean action and also Minkowski action, you try to obtain this kind of expectation values. Say real-time T0, but at some finite temperature beta. So you often, to do this kind of calculation, you often have to have both real-time evolution, but also imaginary time extent. So your T contour takes this kind of, for example, L shape. We have this first go forward in time, and then go back in this term. And then you now take this imaginary time extent to have a sort of finite temperature. But anyways, so as you can see, for example, in this term, because your distribution is now e to the I times the Minkowski action of QCD, this distribution is not sort of real positive valued. So you cannot use this function as your distribution function. It has to be real and positive if you want to sample from it. Or if you have a finite density, then now your this part, which is Euclidean distribution, also has takes a complex value, so it has a sign problem.
Probably want to,
Huh?
probably want to flip the.
Oh, okay. Yeah. So in any case, either at the real time or like at finite density, you cannot simply sample your configurations for the quark fields and gauge things from these distributions, and then that leads to what's called the sign problems. So this sign problems prevent us from computing many things, like I said in the previous slide. You cannot do real time, you cannot do finite density equation of state. So this is like a big issue for decades. So of course, there has been a lot of sort of methods proposed to address this issue. And then as you can see on this list. And there's a lot of them, but I think it's fair to say that none of them has been the solution to lattice QCD sign problems. And well, it's true. Yeah. Yeah, and then I'm going to talk about two methods today. And both of them are sort of the cousins of what's called the manifold deformation methods. It started around this year, but has been sort of generalized and also using like machine learning techniques to sort of address, for example, like finite density sign problem in Thirring model. And so what I'm going to talk about today are both related to, for especially this what's called sign problem, sign optimized manifold that's been done since 2018, and so Scott's involved in that. So this is my what's called table of content, schedule. What's it? Yeah. Any case, yeah. Today is my talk schedule, which is I'll first talk about what's called complex normalizing for this method. This is a method that is sort of very equivalent to the manifold deformation method. I'll explain why later. And this is kind of method that involves some machine learning techniques. But there, like when we worked out this method, we found that this method may not be sort of good for especially like finite density sign problem. So we sort of generalized this method to move to this what's called subtraction method. This is sort of a tentative name. It's not a official name yet, but so I'll explain why with this new method, not only the real-time sign problem, but also the finite density can be alleviated enough. So just to start from the normalizing flows. What is normalizing flows? So I'll first talk about the case where there is no sign problem. So in this case, I have this distribution with the minus S, which is real and positive valued. And normalizing flow is a map from say Y in your fields in your system to some different variables X, such that when you apply this map from Y to X to this distribution, your Boltzmann factor, you get the Gaussian distribution. So you start from some like non-trivial distribution into the minus S of Y, and you apply this map, you get this Gaussian distribution. So if such a map exists, then using this map, you can now compute expectation value space very easily. It's because you can simply, so this is what you wanted to compute, you sample these Y fields from your real positive value distribution, and for each of those configurations, you evaluate your observable and you get the expectation value. But instead of doing that, I just substitute Y, with X using this map, and I'll get this now Gaussian distribution, which you can sample from very easily. You don't have to do Markov chain Monte Carlo sampling. And now you can evaluate this expectation value. So this has been sort of studied very sort of intensely in the last several years, because like I said, if you could find such a sort of nice map that maps your Boltzmann distribution to a Gaussian distribution, you can accelerate your like lattice calculation like very well.
This is S of Y is constrained, right? It has to be a function that goes to 0. at large Y.
Yeah, it has to be normalized. I mean, yeah. Because the Gaussian distribution also. Yeah. So you cannot find, for example, the normalizing
Unbounded function.
right. Yeah, scalar field negative lambda you cannot find. Or if you just if you have just define your theory on the scalar field, in the real axis, then yeah, you cannot. There's no. But we'll talk about this later because that's the sort of main topic of this talk. So this is a nice thing. And also one thing I should say that, yeah, like if you have like normalizable distribution, then such a map always exists. Yeah.
You say some distribution. That's why.
Okay, sorry. Yeah. For yeah. So now I want to generalize this method to our case where the distribution function is now maybe not just real, but could be imaginary complex valued function. I'll just define the map in the same way. It's a map again from like x to or y to x or x to y, such that on one hand, we have this nice simple Gaussian distribution, and on the other hand, we have this distribution e to the minus s with the field y. But like you can see here, because this e to the minus s is complex valued, you should expect that this map wouldn't map the x to y that is real valued. It would like map this x to some complex value y in this complex kind of y. So by sort of finding such a map that sort of satisfies this equation, you are sort of drawing a sort of new contour of integration in your complex kind of y. Nevertheless, if you could find such a map, then again, in the same story as the last slide, you can now compute some sort of expectation value by replacing this e to the minus s of y with this Gaussian distribution. But like again, because we now change the contour of integration from this real axis to a contour in the complex plane, do you know if you get the same expectation values? Because it's different contour, so it's not obvious. And so there are some constraints to this map or equivalent to this kind of new contour that it has to satisfy some conditions so that this map gives you the same correct expectation values. So there are three conditions. So again, like I said in the previous slide, I changed the contour from the real axis to this contour in the complex plane. And I want to make sure that the expectation value that's correctly computed on this real axis is the same as that of the manifold, this contour. And the three conditions are, first, this new manifold has to be a sort of continuous manifold. So I don't want to have any sort of break in the middle. And second of all, I want this manifold to be in what's called asymptotically safe region. So I don't want this manifold, the end of this manifold, to be sort of far away from this real axis. So this is the region where this e to the minus s sort of goes to 0. And third, I need both the e to the minus s and this e to the minus s times O to be holomorphic functions between these, everywhere in this region between this real axis and this point. And when those three conditions are met, Cauchy's integral theorem guarantees that you'll get the same expectation value from both real axis and this deformed contour. So when you're sort of trying to, so in data, we'll try to find these either contour or equivalent to those normalizing flows. But in this process, we have to sort of guarantee that we get this kind of conditions in our algorithm.
So S of Y and S of Z are not the same functions though, right? You're just using S.
Yeah, sorry. Y, I meant for Y, it's a real axis. This is a very much function, but Z is kind of, I'm sort of parameterizing the contour.
Right, I mean S. Do you mean the same?
Yes,
function?
same as, yeah.
Okay.
But you complexified your field.
Okay, I see.
Another question. So what are the asymptotic line that you define?
Yeah, it depends on what your e to the minus s is. Yeah. This is the region where when I sort of take y to like infinity or minus infinity, like sort of it goes to 0. So if it's far away from the real axis, it diverges. And then what I'm doing here is that I'm drawing this contour, this like closed contour between the real axis and this new contour. And I'm saying that within this region, the integral also has to like go to 0, meaning that these two contours give you the same answer. But if there's any sort of finite value here, then I cannot say they're the same answer because these also contribute to this integral on this closed contour. So I have to make sure that the e to the minus is vanishes in those two regions.
So the integral has to converge. So like your Boltzmann factor has to go to 0 at infinities. So that's this great is.
Yeah, so coming back to this normalizing flows or complex normalizing flows, we now want to think how we can sort of either sort of more like theoretically or more numerically, algorithmically, how we can construct such a map, normalizing flows. One way we can sort of imagine how to do it is to say, let's say like my action, this is s of like y and then parameterized by lambda t has the same sign problem. And to this like particular s that I want to solve the sign problem for, I'll prepare a family of actions parameterized by this lambda. For example, I can say that s equals y squared plus like lambda y to the 4, where lambda can be like some complex values. Then in this family, I'll have both this original thing that I'm interested in, but also this sign-free action. So the e to the minus s of this lambda I is positive and real valued. Then, like I said, for the normalizing flow case, when there is no complex things, the normalizing flow for this lambda I, when there is sign-free, normalizing flow always exists. So there is always a map from this e to the minus s to the Gaussian distribution. And let's suppose, I assume that this is assumption that this normalizing flow is also an analytic function of this lambda parameter. Then now by doing analytic continuation from this real valued lambda to another lambda, which is now complex value, I can just generate a normalizing flow. And I'll get to this normalizing flow, which is now a function of this lambda of t. And now I have created normalizing flow, which is for this original action that I was interested in. And using this normalizing flow, now I can do the Gaussian sampling to compute expectation values without any sign problems. So this is like one way to sort of see how one can sort of imagine the existence of normalizing flows in the case where this action is complex valued. Because for the sign-free case, it is really sort of theorem that normalizing flows exist, but for this complex case, it is not obvious question. But this is a very sort of simple sort of picture with many sort of holes in it. So for each theory, like we have to sort of think, okay.
Remind me what F is.
F. F is the normalizing flow from like y is your field in your action, and x is your corresponding Gaussian distribution variables. And this is a normalizing flow is a map from like y to x, such that you can turn this e to the minus s of y to a Gaussian distribution in x.
So is there do you actually solve for F given
Yeah,
y and the action, I think?
we can do that. Yeah. So in our like previous paper, we actually did sort of perturbative calculation for finding this kind of f of x for scalar field theory. But it was not a fun task. Yeah.
But I mean, I would think it's hard, and this is what you would have to do in order to find the right contour, right?
Yeah. So what we ended up doing is to don't think about analytical solution to this f of x, but more like do numerical search, which is how it's related to the sign optimized manifold. I'm not going to talk about the details, but instead of doing analytical calculations, I just prepare a family of ansatz for this map, and then within that family I search for the best.
Okay.
And then hope that that has a towards, better sign, better like smaller sign. So, yes, so maybe, so you have to think, okay, for, each theory that we care about on the lattice, for example, scalar field theory, like SU3 gauge theory, or like in the end lattice QCD, do such like good complex normalizing flows exist. If you could find them, then that means you have solved the sign problem. So you can compute those observables without any difficulties. I think my current sort of guess is that for those bosonic field theories on the lattice, they're like probably like perfect, the normalizing flows. But for lattice QCD, because of some reasons with the fermion determinant, there will be some difficulties, which is why we started talking about the second method, which is the subtraction method. But first I will talk about those two, this kind of bosonic case, because there we can do well with the complex normalizing flows. So like you said, it's kind of a pain to try and find normalizing flows by hands, because you have to solve like one equation for a very high, like large number of degrees of freedoms, like which are your fields on the lattice. So instead of doing that, we decided to prepare a family of like large family of those candidates or those normalizing flows, represent them with this network, in the machine learning context, and trying to find, map in this family which satisfies this definition of the map the best. So of course, you can see like, again, the normalizing flow is a map from X to Y, so that, on one hand you have this Boltzmann distribution, on one hand you have Gaussian distribution. So the input is going to be, for example, X, and the output is going to be Y. And we have some internal like layers, which can be sort of linear rotation of X, or there are also some nonlinear activation functions that sort of making some changes to these inputs, and it gives you some outline, and you get map. So the cost function is simply like this minus this, because we want to find a map that satisfies this equation, the definition for the normalizing flows. So, but of course, the cost function cannot be a complex value, so we have to take some sort of absolute value. One caveat is that when you try to do this kind of numerical search for the normalizing flows, you cannot get the exact normalizing flow. So the normalizing flow, you get some network, and you try to do that. You try to do the sampling using that network, and then, but because this normalizing flow is also not a perfect one, you have some sort of different distribution in the end. But still, to use this kind of approximate normalizing flow, now you have to do some sort of reweighting. So this is the original expectation value is what I want to compute is like this one. But the only thing I have access to is this induced distribution function by this approximate normalizing flow. So I will just simply sample y's from this e to the minus s induced, and then for both numerator and denominator, I compute two expectation values, and then just divide one by the other. So this, in principle, is supposed to give you the correct value, and this does, but there is a problem. It's just that suppose I didn't do a good job in finding a normalizing flow, so that, for example, if this distribution I get by this approximate normalizing flow only did a good job for finding sort of the absolute value of this sort of physical Boltzmann distribution function, then if you look at the denominator, it looks like what you're computing is the expectation value of this phase of the Boltzmann factor by this quench distribution, which is this e to the minus real part of s, which we often call the average sign. So what you're doing here is that you sort of sample a phase from this unit circle and sum them up to get some small number. And you can naively see that as you make the lattice size bigger and bigger, the average sign sort of drops exponentially like with the volume, because you can naively think that your path integral like in sort of factorized to like local terms, because lattice theories tend to have only local interactions. So if you, let's say for this like one size of the lattice, I have this like I had this average sign of A, then if I put two lattices together, my average sign is now A squared, so it's smaller. And if I have now B times larger lattice, then my average sign is going to be A to the B. So this is bad, because by only sampling the numbers that is order 1, I'm trying to estimate the a very, very small number. But I still want to resolve this from 0, because I'm dividing the whole this thing by this very small number. And to do so, I need to have this exponentially large number of samples. And this is very difficult. I mean, we cannot do that. So to do a good job in this business, what you have to do is to get this phase part of this eta minus correctly, or like well in this induced distribution. But in any case, yeah, so we tried this method in what we call complex coupling model. So this is a scalar field theory on the lattice. So I have as an action, I have, for example, this mass term, which is pi squared, but I also have this hopping term, sort of kinetic term. And I also have this pi for interaction term. This is G is often like, real values, but just to introduce a sign problem, we made this G to a complex value. Then the network, which sort of represent this normalizing flow, is going to be some function from X to pi, which have, and then we sort of divided them into like real part and imaginary part, so I have two functions. But it starts from like X, and I'll output some sort of term that pi, and I have this like a linear piece, but also I have this kind of hidden like network with some like internal like layers, like I sort of showed in the several slides ago. This one, and this is, I always describe like a matrix. So you just sort of mix up your input X, and also this sigma are what's called activation functions. It sort of acts on like each single node and sort of do this nonlinear transformation. And by sort of designing some network, I have now prepared a family of possible normalizing flows. Now I want to find the best one out of this family. So we did that. So first, just to start, we tried like 0 plus 1 dimensional system. So I have only 10 sites. So I have only like 10 phi's. And let's say I set the mass to like 0.5, and then I see how the training went. So this is the plot where I set the coupling to be like coupling to be the 0.1 plus I for G. And for the linear layer, so I have either nothing, or I have this single layer, meaning this, and also only like one set of internal layer. And then see, as I sort of train this network, how does the average sign changes? So just so you know, when the average sign is 0, it's really bad. And then if it's 1, it's very good. So you can see that it's not like really bad from the beginning, but for the like linear layer, as I showed trained, the average sign went up very quickly and just stay there forever. This is the linear layer, so it has like smaller candidate normalizing flows. Then I added like one more layer, which is for this red line. Now you can see that as I train more and more over time, the average sign sort of increases and fluctuations because of the design of the optimizer. But in the end, it got better average sign because larger network has more candidate for normalizing flow. So you tend to have better normalizing flow in the end. And just to check that our normalizing flow is getting the correct expectation values in this system, we just check that now we computed, not using this normalizing flows, we computed this expectation value of pi squared for different imaginary part of lambda, and then see that they just agree with the exact values. So the method actually at least gives you correct expectation values. But this is a very sort of small system, so the question is whether we can scale this up to like a larger lattice. But before we move on, I just wanted to show you a plot that I think is cool. So this one sort of nice thing about this normalizing flow is that you can compute the partition function itself. So we did that. This is a plane of coupling lambda, real and then imaginary axis. So on this, positive real axis of lambda, you don't have any sign problem. And of course, if you now, for example, want to study a system here, but still define that your phi's p of phi takes value from like minus to plus infinity, then that partition function just diverges. So the way we defined a theory right here is to just do analytic continuation from this real axis to rotate. And we computed this partition function for, again, the sides of 10, we moved to 0.5, and then have only that one internal layer, and then see how the partition function looks, on this plane. Because there are interesting things, like when the partition function like vanishes, that gives you some information about the field theory. Unfortunately, as you can see, you couldn't find any zeros of the partition function in this Riemann sheet, but if you maybe go down to the next sheet, maybe we could find it. And to do so to get this plot, we studied like many points on this like plane of lambda, and the way we did it is that we, for example, train the normalizing flow for like here, like one small point here, and then using this as ansatz, we now trained the normalizing flow for the nearest neighbor along the next lambda. By doing so, we could have sort of trained this network very easily, and then could have get this plot. So I think on this plot there are like hundreds of different normalizings for so different lambdas. So we moved on to like 1+1 dimensions, because they're like the again, as I said, the lattice is bigger, so the average design problem is worse. For example, like you can see without any sort of normalizing flow method, you can see that as you change the number of sites from like 10 to 80 in this log scale plot, the average sign goes down linearly, meaning the exponential in the volume. But with this trained network, with only like linear contour. So I think in this case we use only the like linear transformation of this network of this like contour from like real axis to just linearly to the complex plane of phi. You could see that it's still like straight line, but overall like the average sign was like much better compared to this real plane. And yeah, we did a square price with this. So this is sort of to show that for some reasons that I don't really understand, for this complex coupling case, even if you went to like 2 dimensions, normalizing flow did pretty well, even with this tiny, very simple like ansatz for the normalizing flows. It's just a linear like rotation of your field, contouring your field. And I don't really know like why it did this so well, to be honest. And just to complete the story, we did the same thing of finding partition function for this 1+1, 2, and then so if there is any zero of the partition function, you should see sort of surrounding arrows, but you don't see it. So again, there's no zero on this corner of this lambda. Again, this is done for linear transformation. So the network is very simple. It was very easy to train. Yeah. Again, I don't know why this worked so well. But so this is the whole thing we did for the first paper. And the obvious sort of next step for this method is to now, for example, complexify this M so that you actually study the scalar field theory in Minkowski. So I sort of tried that, and compared to this complex coupling model, it was way more difficult to find a good normalizing flow. And then I haven't sort of figured out a way to get the average sign better for this Minkowski scalar field theory. But this was the original motivation for studying this. But then was to sort of get to the scalar field theory Minkowski from this was sort of first step. But apparently this was like for some reasons like too easy, and then Minkowski scalar field theory seems to be very difficult. I don't know why. So this was the whole story about this complex normalizing flows. I'm not sure about the Minkowski bosonic field theories, but at least for the complex coupling case, it worked pretty well. So I already said that I may not work well for the scalar field theory in the Minkowski, but we should still ask, okay, would it work for lattice QCD? Because that's the ultimate goal for, of this whole business, right? And there's no reason that we don't think that this kind of complex normalizing flows or equivalently contour deformation would not work well for this lattice QCD because of fermions. So to compute to the lattice QCD, we tend to sort of first we start from quarks and the gauge fields in this path integral, and we integrate out those quark fields. And we are left with this eta minus s, where s is the action of gauge fields. And I also have this determinant of this Dirac matrix, which is now again the function of u, and I just put a form here. But what's important is that this determinant can vanish in the complex plane of u. And then this is kind of, we think it's about that this distribution eta minus s times determinant can vanish because of the following reason, which is that so you can always get locally perfect manifold, meaning that you have no like local phase fluctuations. But when such a sort of locally perfect manifold intersects with a point where this distribution vanishes, there's no guarantee that phase don't change between those two local segments. So even though you have a locally perfect, even if you have no sign problem locally, you may still have a global sign problem because the two segments can sort of cancel with each other. So this is how naively why we think that unfortunately for this QCD, we may sort of find that we intersect this kind of zeros so that we cannot get away with the global sign problem. Another way to see why zeros are bad is from normalizing flow point of view. For example, is to look at this kind of very simple model. So my model is now a very one variable function, like eta s minus this being just cosine of theta plus some number epsilon. And then I take theta from like 0 to 2 pi. Because now I'm on the sort of closed contour, I define my normalizing flow to be a function from cosine theta plus epsilon to like just constant distribution on this x. Then you can find that the inverse of this normalizing flow from say theta x is this kind of function. So you can see that when epsilon is bigger than 1, then it's this blue distribution. You don't have any sign for it because the distribution is always positive, right? But then when you lower this epsilon to like 1, now the distribution touches 0. Still no sign problem. But then when you now lower the epsilon to 0.5, for example, now you close this 0 so that the distribution is positive here, but negative here. So there's a sign problem. And if you look at this normalizing flow now, so then the important thing is that this distribution closes 0 and 0. And if you look at this normalizing flow, when there is no sign problem with the blue line, or there is good normalizing flow, and exactly at epsilon equals 1, still fine. But now then you look at the case where you have this intersection with 0, when epsilon is, for example, 0.5, you see that it's has this sort of binding curve, meaning that this is not a sort of single valued function. So you cannot use this normalizing flow as your map anymore, because for each x, you have multiple values. So what do I mean by a map for this case? So this is another way to see why zeros might cause a problem. It's essentially that when this distribution, eta minus s, vanishes, meaning that this part vanishes, but it still has to be 1, so this part has to diverge. or this, if you look at theta to x, this slope has to sort of vanish at 2 points, meaning that you have some sort of coming back curve in your normalizing flow. So
is it guaranteed that you will have zeros in QCD, or are you saying you would expect there to be?
I think they are. Yeah. I think I forgot. Away from real print, I forgot. Yeah.
Yeah, the fermion determinant is,
Sorry,
the fermion determinant has it.
zeros, okay.
Yeah, but I don't remember if it's close to the real plane or like depending on mu, like how it behaves.
At chemical potential above some certain amount,
Hmm.
I think is the ion mass.
Hmm.
They intersect the real plane. So changing the chemical potential moves all the zeros in imaginary A naught direction.
Yeah.
And so at zero chemical potential, they don't intersect the real plane, but at large enough, they start intersecting.
I see.
All technical issues.
I mean, is it one-to-one related to the fact that there is a sign problem? Or,
Not 1-to-1, but maybe like 1.5-to-1. Proof that there's no sign problem at zero chemical potential involves
It's a hermitistic.
yeah, exactly. And on the way you say, you
Yeah.
accidentally say that there can't be any zeros of odd order. Like that pops out immediately.
Oh, okay.
So somewhat of it.
Anyways, so this is how like we sort of got disappointed at this complex normalizing flows because it may not apply to lattice QCD at finite density. Then like we sort of decided to work on a more general scheme but simpler scheme, which is what we for now call subtraction method, which started from this paper first 2 years ago. So instead of doing any sort of contour deformation to the complex plane or like normalizing flow map, that kind of stuff, let's just simply think how we can modify the partition function to sort of reduce the sign problem. What we can do to this distribution without changing the partition function is to simply subtract a function f of phi such that this f of phi, integrates out to 0. So we haven't changed this partition function, but this denominator can change, and it can change the average sign either like lower or like a bigger, but we can hopefully like find a function f such that the average sign gets bigger so that the average sign problem gets milder. And you can sort of see that this method, subtraction, is a very simple generalization of this contour deformation. Because what we did in the contour deformation is that we started from this real plane, and then we got rid of this real plane and we introduced this contour. But we know that the integration of this function e to the minus s on this contour vanishes. So in here, e to the minus s on m minus e to the minus s on r is 0, meaning that this is like one kind of subtraction function. And if you subtract this whole function from this, then of course you get this, you're left with this contour deformation. So this is a very simple generalized version of contour deformation, but a very nice thing about this subtraction method is that unlike this contour deformation method, subtraction always exists for like whatever theory.
so hang on. So hopefully this, why do you want that?
Because I want the average sign for this subtracted distribution to be better than that of the original one.
I see.
Yeah.
Okay.
Yeah. Yeah, so the nice thing about is that for the subtractions, for any functions, any distributions, perfect subtraction function, which sort of get rid of the fluctuation, always exists. Whatever scalar field theory, bosonic, or finite density QCD, it exists. The model is to find it, which is a big problem. But just to sort of show naively why it always exists, let me just go back to this example, cosine theta plus epsilon. what do you think is the sort of perfect subtraction for this model? Like when we were talking about this this method, I was like, I know, epsilon. I got this wrong. It's actually not epsilon. You just subtract cosine theta. Then you're left with epsilon, which is just a constant function. There is no sign. Cosine theta integrates out to 0 from 10(0) to 2π, so it's a valid subtraction function. And then more generally, for any eta minus s distribution, this you can, for the one example of a perfect subtraction is something like this. This f of phi integrates out to 0, and if you subtract this from eta minus s, you get rid of this whole thing, and you're left with a constant function. But of course, this is not a unique solution. There are like many other possible functions that sort of integrates out to 0, but still give you no phase fluctuation in the end. So again, how do we find them? To do so, first we want to impose that this subtraction always integrates.
So how does this get around this other problem that you had with the contour where you were going through 0 and so on? So what does this achieve?
Well, I mean, so this was just one example where even if you have 0 in a vanishing eta minus s,
Okay,
you can always
positive. Is that...
Yeah. So imagine that you subtract this whole thing from eta minus s, then you are left with this constant part, right? If it's a constant, then no matter what it is, it's there is no sign for it. It's a sort of uniform distribution. So how do we find them? We first again want to impose that this kind of subtraction function integrates out to 0. So we write down the function as sort of divergence of a vector field on this field space. Then by divergence theorem, we can guarantee that the vector field, the subtraction function integrates out to 0. Also, when we are trying to find the subtraction function, we notice that the because this eta minus s changes its value like a lot from like really small number to like a big number, we needed to sort of scale the vector field in the same way. But this is kind of minor detail. And again, so okay, we modified the partition function, but we never talked about how we do the measurement, which is what we actually have to do. So we went through several like ideas of how we can sort of use this subtraction method to actually also have a good way of measuring those expectation values without introducing any other sort of noise problems. I'm not going to talk about details, but we ended up like one method which we used for this results in the next 2 slides. And then again for the subtraction function, like I said, I want to find a vector field that sort of gives you like a good subtraction function that reduces the sign problem. So we again like represented this vector field using network right here. And then because I'm out of time, I will just show you like 2 plots, very preliminary results. But so we checked, we are trying to like test this method on fermionic system Thirring model at finite density. So for example, it's a very small lattice, but 6 by 6. I think I skipped the action slide. This is my action with a Thirring model with the scalar fermion. You can see that when you don't have any subtraction, the average sign sort of gets worse as you increase the chemical potential. But while by doing this subtraction, you can at least pull up the average sign a little bit, which helps you compute the expectation values with smaller error bars. But also we sort of check that either with this like no subtraction or with subtraction, I get the same number density for a Thirring model. So at least the method is giving you the correct physics. And also another thing we should sort of explore is that, like we saw in this complex coupling case, when you sort of prepare like a larger network, that means you have larger family of candidates for your normalizing flows or like vector fields. You hope that you sort of expect that you should get better vector field, meaning you get smaller, larger average sign. So you can see that. So this is what we did, which is that for like different number of layers, internal layers for the vector field network. See how how well they do. So sorry, I forgot to sort of put thing, but this is also average sign. And as you increase the number of layers from like 0 to 2 layers, you can clearly see that the average sign goes up. So it's happening. But for some reasons, I don't know yet, but from 2 to 4 layers, it didn't increase very much. Also, this scale means how long you train the vector field. And then as you increase the scale from like 0.13, so from a shorter training to like longer training, that also helps. Yeah, because by doing longer training, that means you're exploring larger space of your parameters in your vector field network. And so these are the two sort of methods that we have worked for this sign problems, either like real time or a chemical finite density sign problems. But especially for this subtraction method, because we at least know that the subtraction function exists, perfect one exists. So if you can't find it, that doesn't mean that it doesn't exist. It just means that your method has a problem. So while we sort of improve numerical methods to sort of get those better and better subtraction functions, there are the various systems we can attack. For example, this is Thirring model is what we're doing now. But for example, we can apply this method to just spin systems, which has a discrete sort of degree of freedom. We can do it because unlike contour deformation, which needs sort of continuous field, it's just a subtraction. So it's easy. And that hopefully young viewers to see in the future, I don't know, many years ago, or many years later. But also, so this is the sort of systems we want to tackle. But like you have seen, I think, in the last several slides, this method is kind of new and then still like under development. So there are many things we should think about. For example, in this slide, I showed how one can numerically find those vector fields, like subtraction functions. But you can now think, because subtraction is such a sort of very simple sort of action to your modification of your path integral. Maybe you can think, if you could analytically sort of nail down, okay, what is causing the sign problem? I don't know, by, for example, lattice QCD, if you can do some heavy dense limit, or like, I don't know, if you can get some insights from, I don't know, EFTs, then that can help. So these are the things that we are thinking, and then, or maybe you have to combine both analytical and numerical methods to get those good vector fields or subtraction functions. But these are the sort of things we are trying to do in the future. Yeah, that's it. Thank you.
Any questions?
What base time dimensions are you going to be using for some of these other models? For the 3+4?
For Thirring, like we're doing just 1+1.
Okay.
Spin hopefully 2+1. But I mean for well, the method simply applies to the extent can be sort of used to like either 1+1 or 2+1 higher dimensions. But the problem is really that can we have sort of large enough search for those either like normalizing flows or vector fields so that we can get the average sign like large enough, because for this larger system we have worse and worse sign problems. And then I don't know if this method can be applied to like those larger systems with our current numerical power.
So without this neural networks, it's hard to search for these. Right?
I don't know. For example, like for this Heisenberg spin system, like let's say you have only like one spin, so like 0+1 spin system. Of course, you know how to solve it, but at least I could write down also corresponding perfect subtraction function. So that was a purely analytical work. And we know, for example, for that transverse field Ising model in 1+1, there's a solution to it in a sort of fermion because it's free fermions. So we think that we can get also a subtraction function from that. It's also analytical work.
Right, but you're hoping for like something, I mean, this is very ambitious, right? Your fourth point.
Huh?
The
Yeah, this
fourth
one?
point is ambitious, right?
Yeah, but
But you would need neural network for that, right? To search for the right
think-
subtraction function.
I don't know. I think in the end, probably yes, but it helps a lot to input information we know about QCD to the network itself, so that we can, we know, for example, if there's any piece of subtraction function that we know it's good, that we can feed that to the network, and that helps. But otherwise, we have to do a very like blind search, and then I think that's going to be hard. Okay.
Thanks.
Yukari. I was thinking, I just potentially had problems in general, like if you were not using a neural network,
How many people were?
how hard would sinus search?
Today, 2 people.
I mean, I'm trying to understand, is it as hard as the sign problem if you were not using
Yes.
this?
You're in.
Yeah.
Carol?
So
No,
your question is whether you need exponentially larger.
See, I don't understand why you have to give me why you don't live search.
There's like
a
website.
So if you use the line search, it's basically how the
open.
exponential
You mean
So
putting
you
the. No, not the Zoom ID. Not the Zoom ID. Just the protection is the same. Because not everyone can go inside there.
But if you did apply.
It's convenient for me if I can't be here on
Then
campus to be
is
able
the-
to attend
is the
online,
subtraction
which is what I've been doing most of the time, as you know.
as hard as the sign problem itself.
So I try to make effort to get to more in real, be here in person, so.
Yeah, I mean, there's no guarantee that it gets better or worse.
Okay, I mean, you may have to like wait the age of the universe to get to the.
Yeah.
Thank you.
I mean, if you do a pure like random search, but the nice thing about network, you can actually so that it has larger and larger. I skip